get started. All right. Hi, everyone. Thanks for joining. This is Open Source Antibiotics meeting on Friday, the 18th of March. So we have a short meeting today that is intended to focus on a couple of things. One is going to be, I think, Daniel's recent chemistry. Two is going to be Alex's tox and DNA binding work. I think she'll be joining us in a minute. Three was going to be Lee Graves's mechanism of action work. I think he's not quite ready to come to the meeting to present the data today. So the plan is currently to talk about that at the next meeting, which will be on April the 1st. And that is not a joke. It will be on April the 1st. No. Daniel, you called it Lie Day earlier. That was really amusing. So in Brazil, it's called Lie Day, which I prefer, right? But, so it'll be April the 1st. It will be, I think, the next meeting after this. And hopefully Lee will be able to come along and talk about the mechanism of action stuff. All right, but while we're waiting for Alex, Daniel, do you want to say a few words about some of the chemistry you've been doing?
Yeah, I can share my screen here. Just 1 second. So I have made some progress. The first compounds that I could synthesize is the
Wait a minute, sorry, one thing. Just as a background to remind myself, so the molecules that you're showing as targets here originate because we liked compound 975, right? It came back as potent and with a nice clearance data. So we're exploring that motif, right?
Yeah, we would like to synthesize other compounds with better log D. So we're playing some few compounds. I have here in the bottom. So the 4 compounds, I'm still waiting for the chemicals. Maybe next week I will have the chemicals. So I'm currently working the top ones. Number 6, I already finished it. It's no problem to synthesize the compound and purify.
Daniel, your audio is a little bit tricky. Can you put the microphone closer to you or anything?
My microphone is actually...
It's in the earphones, right? Okay.
Yeah, earphones.
No worries. Please go ahead. That's fine.
So also the first one, having a state-free group, I didn't have any problem. The problem is when I have the pyridine, the reaction didn't work. So I changed the catalyst. I'm using now palladium tetrakis 3-phosphine. The reaction is working, but I'm having some problems with the purification. I always get start material plus product. So I did normal phase and reverse phase, and then still having that problem. Microwave conditions is better than refluxing. So, but I still have no full conversion of the product. Yeah, I'll try to do some more purifications and see if I can get any, at least like milligrams of the compound to test them. So this is basically the progress.
Okay, and that's so that one's done. The other 3, 6, 7, and 8 are you're working on, and the ones below you're waiting for the reagents.
Number 7 and number 8. So I tried a couple of times the reaction using 2 different catalysts, microwave conditions, refluxing. So the problem right now is actually the purification.
Okay.
I'm trying to solve this problem.
Okay. Pretty nitrogen heavy, I guess.
It's too polar. The number 7 is really polar compound. And the separation is not good even in reverse phase.
Okay, good. And is the materials for the bottom 4, the commercial materials, any delay there, or is it just the usual? Is there a problem with the supply or anything?
We order from Apollo.
Okay.
3 days ago.
Oh, fine. Okay, fine.
Yeah, I guess next Monday. So I guess it's gonna be here. We ordered all the 4 boronic acids.
Great. Okay, those should be good.
Yeah.
All right. Thanks, Daniel.
You're welcome.
All right, and hi, Alex. We were just talking chemistry before you came. Oh, are you with us, Alex? Your video is frozen.
Hi. Sorry, I'm late. I just had Yeah. Can you hear me?
Yeah, I can hear you. Your video's frozen.
Can you hear me?
Oh, that's all right.
Hello?
Yeah, we
Hello?
can hear you. There's a bit of a lag there. Okay. Sure.
Yep.
Yeah, the usual problems. Maria, while we're talking, did you have anything you wanted to update from your lab, or are you just here to catch up with what's been going on?
Oh yes, I have. Just a second.
Okay, great. If you wanted to share something, that's awesome. Hi, Alex. We're just going to talk a bit more chemistry before you get started.
Sure. Can you hear me now, though?
Yeah, slightly better, I think.
Okay, cool.
I think Maria's just going to share a slide and then we can talk talks. Are you ready to go, Maria, or do you want more time?
I don't know, but my PowerPoint is not opening. It's so slow. I don't understand.
Okay. All right. Should we cut to Alex first and then we can come
Okay.
back? Okay.
Okay.
All right, Alex, if you're happy to talk about what you've been doing, that would be really great. You're muted, by the way.
Can everyone see that?
Yeah.
Yes. Looks good. You're muted again for some reason. I don't know why. Its computer's deciding to mute you.
Yeah. Okay, cool. Everyone can hear me now, right?
Yeah, all good.
Yeah. So sorry, I'm not here too often. But last time we were wondering why is it that these compounds are so toxic, and we hypothesized that maybe they're binding to DNA. Right. So what I've been doing was to test that hypothesis, and the way I've been doing this, I designed some DNA sequences which are complementary to each other, and they have fluorescent donor at one end, fluorescent quencher at the other end. So when the sequence is annealed, then it will be complementary to each other, so there will be no fluorescence. If there's something that comes and interferes with the binding, then we should see a change in fluorescence. So what I'm showing on this slide is what happens to when you just cycle the molecular beacon, as it's called, through different temperatures. And from this, you can get a curve that looks like this, where you have temperature and then amount of fluorescence observed in a particular channel, whether it's the donor or the quencher channel. And then you can plot the first derivative of that and find a peak, and that is your melting temperature. So for this particular sequence of DNA, I measured 56.36 degrees, and I wrote here an interval with 3 standard deviations. So the next thing was, okay, so how will I know that it doesn't work? The next thing that was important for me was to include some sort of positive control. So in the absence of better molecules, I went with doxorubicin, and you can see here that I am adding increasing concentrations of doxorubicin to my DNA, and then we're measuring again the change in fluorescence, and as a result of that, we can also measure the new melting temperature of the DNA. So you can see there's a clear shift towards the right, suggesting that doxorubicin is stabilizing the DNA duplex, which results in it melting at a higher temperature. So this makes sense to me. So we can just go ahead and test some molecules. And I decided to go with 821, 861. So 821 is very toxic, 861 is not toxic. And then tamoxifen and doxorubicin, tamoxifen is another control from the COAT protocol. So what this graph shows is, in my opinion, in the absence of anyone else's opinion, is that neither of these anti-MRSA compounds are interacting with the DNA, at least not in the way that IC52A21, which is the most toxic one that I've tested. And that's it.
That is very nice data. Nice experiment, nice result. I guess, so what, is it possible that the molecules could bind DNA and not alter the melting temperature? Not really, right?
So I have a few other, well, I basically bought 3 different DNA sequences. You can design these as you, well, there are some guidelines, but and depending on how much GNC they have higher or smaller melting temperatures. So this one that I've tested here is the one that this melts most readily. I can see whether with a DNA sequence that is more stable, whether that makes a difference at all. The other thing is, and these are questions that I wanted to ask Gary, but I haven't managed to speak to him or pick his brains yet. Whether we should be going higher in concentration, and generally, yeah, whether the variability of this data is fine, because I mean, sort of the curves don't quite overlap, although it's supposed to be the same thing. When you calculate the derivative and fit the peak, you get something very, like the deviation is not high, but in terms of the absolute intensities and that, I think I need to check that it's all fine, but
Right.
it makes sense to me. So it's, yeah.
Yeah. What about?
I was going to say,
say again?
Apologies, I should remember this, but what were the concentrations in which you actually saw toxicity?
So yeah, so this is micromole concentrations that I'm here, 0.1, 0.5 to 4. All the concentrations that we test at are, because I do that in mg per mil, so maybe I can think 10, 1. It's probably lower than these concentrations. I think it's around 1 micromole.
Okay.
The highest one.
Yeah, that's fine.
And so the way the experiment runs is you raise the temperature, right?
Yep.
And do you ever just then cool it down and check that it goes back the same way?
Yeah. So you also cool it down, yeah.
Okay, and so with the cooling down, I mean, I'm just trying to think
I haven't looked at that data. But...
if it bound single-stranded, would that, but not double-stranded, would that
But so then
that?
it's irreversible binding. I think maybe.
Or it changes the temperature at which the DNA re-anneals. So if you did the reverse and went from high to low, would that reveal if there was a binding with single-stranded? I guess would be my only thought.
Yeah.
I'm not trying to.
No.
presume,
No.
no, I'm not trying to presume what the mechanism is. I'm just wondering about what kind of interactions we might be seeing, and I don't know.
I think that would suggest then that it has high affinity though, right?
Yeah.
And we should be seeing a significant difference when we go up, right? Because if it's, I don't know.
Yeah, because then it would encourage the unannealing, right? Yeah.
I think this is how I understood. I don't think people, or at least when I spoke to Gary, he didn't seem to bother about the going down data. It's definitely done in the experiment, but.
Oh, is it?
Yeah, so I definitely do the cooling down before, but so I can see whether I have access to that data. But
okay, great. That'll be interesting. I mean, the first diagram you had, showed an annealed section and then a loop which wasn't annealed, and I guess that would also be important. So there is double-stranded in the middle, but there's a bit where there isn't, where it curves around, I suppose. And I guess that's
okay. I see.
That's realistic.
Yeah.
So if it was binding single-stranded, you'd expect there to be an impact because it would sort of partially unwind it, right? Sorry, it would partially unanneal. I don't know if there's a better word than that, but it would partially unanneal at the bit where you're.
So you're suggesting that it's binding at the hairpin.
Maybe.
Okay.
I don't know. But the data, if you've got it, would show you that for sure. Yeah, if you can get the going down data, that would be awesome.
Sure.
Great, really nice though. I mean, yeah, beautiful.
I'm not sure it's the,
No, it's great.
answer that you're looking for.
Oh, I don't care. Just want to know what's
Okay.
the case. I mean, yeah. Anyone get any other questions or insights on that? It's nice. All right. Well, that's really good. Yeah, if you wouldn't mind just checking on the going down data, and then if you wanted to, if you're happy to when you're happy to send a few of those slides over, we can post them somewhere so people can have a look, and then we can see if anyone's got any other interpretations.
Yeah, and continue to. I think Gary is currently very busy with teaching, but
yeah,
maybe he will become more available in the next couple of weeks.
I think from Monday. And did you want to say anything about talks?
So I haven't plotted everything. I think I have at least completed the experiments, but I still need to plot the data. But so far I haven't seen anything different to what I've shown before. So. Okay,
great. Yeah. The online paper is coming together quite nicely.
Yep, and I need to look at that.
Yeah, no, I mean, we've been sort of tweaking the various diagrams and data and stuff because we really want to, publish something and make sure that all your efforts are appropriately recognized by authorship on a paper. So whenever you can get those to us, we can fold those in.
Yeah, awesome. Thank you.
All right, thank you so much, Alex. Really good. And then just in the last few minutes, Maria, did you want to have a go at presenting something again?
Oh, yes. Okay, I'm ready. Can you see my PowerPoint?
Yep.
Okay, so I'm working on these two analogs, these two derivatives, and the syntheses are ongoing. So I have these two intermediates because I'm working on both the molecules. And I think that in a couple of weeks it should be ready. And in this meanwhile, I want to ask you if you are also still interested in this molecule with the cyclopropyl, because when we sent you the first batch of molecules, these molecules was not included because I had some purification issues. But if you are still interested in testing it, I can try to purify again and to include it.
Your audio was cutting out a little bit there, but the molecule on the top right is something that we don't have enough of at the moment, and you have to remake.
No. I have this, but it's impure, so I have
impure.
to try just to purify again.
It would be it's a nice analog for sure. I think it's a I guess the cyclopropyl is something that we haven't really had in the series before, right? As far as I'm aware.
Okay.
So if you are not going to spend like a massive amount of time on that, it would be nice to have. If you're going to be spending like days and days on it, don't.
No, okay. I try to purify again and to include in the new shipment. So.
Okay, fantastic. And sorry, the two molecules on the bottom right of your slide there are your current targets. So that's on the bottom right. So the imidazole version and then the what is that pyrimidine version? So bottom right of your slide, the bottom right molecule and the one above it. Is that right? So those are your current synthetic targets?
No, because I think that's an error. I think the bottom one shouldn't be a pyrimidine.
Yeah,
it should be a pyridine.
Yeah, that's right. Okay, but those look very interesting for evaluation for sure. I guess I wasn't aware you were making those. Maybe I should be aware you're making those, but I wasn't aware you're making those because those are quite nice. So you're currently progressing through these. You've got 300 mgs of one and 70 mgs of another, and you're trying to get to the end of both of those. Is that right? Okay, great, fantastic. This looks really interesting. All right, that was everything I had. Everything anyone else wanted to say? All right. Great, thank you all very much. And next meeting is on, as I said before, April the 1st. where we'll hopefully get some mechanism of action stuff from Lee. So see everybody then. Thanks for coming.
Bye, everyone.
Bye.